Thus, we see limiting value of fx is equal to 0. Also, limiting value of phi x is equal to 0. Now, by drawing the graph, what we find when x is greater than 2, that means 2 less than equal to x less than 3. Finally, we have got this one. Value of this expression is this one. Now, we see denominator is x minus 1. This is x tends to 1. Therefore, x minus 1 is not equal to 0. Problem I have taken, if limit extends to a fx is equal to limit extends to a phi x, then will fx equal to phi x always? I am going to answer this. You see, fx, phi x, two different functions, but their limiting values are equal. Now, can I conclude fx equal to phi x? For explaining this, I take example like this. Let fx equal to x square, phi x equal to sin x, and a equal to 0. I have taken specific case, fx equal to function x square, phi x equal to sin x, and a equal to 0. Therefore, limit x tends to a, fx becomes limit x tends to 0, x square. Then already we have discussed the value will be in this case 0, and limit x tends to a phi x, limit x tends to 0 sin x, and this is basic limit, value is 0. Thus, we see limiting value of fx is equal to 0. Also, limiting value of phi x is equal to 0. But you see, these two functions are not same. But x square, sin x square not equal to sin x. Only in case of x equal to 0, these two will be equal, but otherwise function x square sin x are not equal. Therefore, fx is not equal to phi x always. Therefore, limit x tends to a fx, limit x tends to a phi x does not imply fx equal to phi x always. Actually, by taking specific values of two different functions, we can explain this matter. Therefore, this problem is solved. Before discussing the next sum, I first define greatest integer function. If fx be a greatest integer function, then the values of fx will be like this. If x lies in between -3 and -2, including -3, then fx will have the value -3. When x is lying in between -2, -1, including -2, then the value will be -2. When x will be within -1 and 0, including -1, value will be value of fx will be -1, like this. Therefore, I can define in brief form, fx will be equal to n when n is less than equal to x less than n plus 1, where n is any integer. This is the definition of greatest integer function. Now we take a sum based on greatest integer function. Sum number, I think, 5. Is equal to this indicates greatest integer function. Now we have to show limit x tends to 2 fx does not exist. How? When x less than 2, that means L f2, that is equal to limit x tends to 2 minus. Already I have discussed, when x is just less than 2, slightly less than 2, then value of fx when it is greatest integer function will be 1. That means it is lying one less than 2 and less than 2. For that, value of x may be taken as it is greatest integer function 1. Therefore, in this case, value will be 1, and R f2 limit x tends to 2 plus. That means here 2 less than equal to therefore the value will be when x is greater than equal to 2, then value of the greatest integer function will be 2. Thus we see, therefore L f2 is not equal to R f2. Therefore limit x tends to 2 does not exist. We can explain this problem with the help of drawing graph. I have drawn the graph of box function here. When x lies in between 0 and 1, including 0, the graph of the box function will be this one, excluding the point 1, 0. When x lies in between 1 and 2, including 1, this segment will indicate fx, excluding 1 point. Similarly, this 1. Now we see, if we consider all this, then these look like steps. That is why we call this function fx equal to box x, also called box function, as step function. Now, by drawing the graph, what we find, when x is greater than 2, that means 2 less than equal to x less than 3, then this is the graph. And it is clear that values are different. When it is just greater than 2, then this segment is the graph of this box function, and when it is 3 or greater than 3, then this is the graphical form of box X. And from this graph it is clear, you see there are gaps or jumps in between these two segments, separately. Therefore, from the graph it is clear, limit x tends to 2, box X does not exist, also called box function, step function, and greatest integer function. Therefore, the problem is solved. Next sum, fx equal to x square minus 2x plus 3. We have to find the value of this one. Actually, I am discussing here variety of problems related to limits. That is why variety sums I am taking. Given fx equal to this one, therefore we can calculate f1 also. Fx therefore f1 1 minus 2 plus 3 . Therefore, we calculate this expression. Therefore, this limiting value will be equal to limit x tends to 1, x square minus 2x plus 1 by x minus 1. Therefore, this is equal to limit x tends to 1. This is x minus 1 whole square by x minus 1. Finally, we have got this one. Value of this expression is this one. Now, we see denominator is x minus 1. This is x tends to 1. Therefore, x minus 1 is not equal to 0. Therefore, we can cancel from numerator and denominator x minus 1. That means limit x tends to 1, x minus 1. Here we mention since x tends to 1, therefore x minus 1 non-zero. Therefore, we can cancel like this. Therefore, finally the value will be 1 minus 1, 0. Therefore, finally I write this step. Limit x tends to 1 fx minus f1 by x minus 1 equal to 0. Follow, in such type of problems, when fx is given and this expression is also there, we have to find the limiting value. First we calculate the value of this expression step by step, and after getting this value we calculate this one, and finally we get the value 0.